All right, today we are diving deep into something absolutely fundamental, the very core of how you think, how you feel, how you move. We're going to talk about the action potential. You know, that tiny, unbelievably fast electrical signal that basically powers our entire nervous system.
So, have you ever really stopped to think about that? How does a decision, a simple thought to move your hand, travel from your brain all the way to your fingers in like a split second? I mean, it feels like magic, right? But it's not. It's pure biology, and it's happening faster than a race car.
And the answer, the secret to all that speed, comes down to this one microscopic electrical event. It's called the action potential. It is the fundamental spark that makes everything else in your nervous system possible.
Okay, so to get this spark, first, you gotta understand the wiring. Our nervous system is built from these incredible cells called neurons, and neurons basically have two superpowers. The first is excitability. That's the ability to get worked up and generate an electrical impulse. And the second is conductivity, the ability to send that impulse down the line. They are literally the wiring behind every single thing you experience.
But here's the thing. Before a neuron can fire off a signal, it has to be in a state of readiness. Just think of a resting neuron as a tiny, fully charged battery, just sitting there, waiting for the signal that says, go.
So how does this little battery get its charge? Well, it's all about keeping two groups of charged particles, or ions, separated. On the outside of the neuron, you've got a whole crowd of positive sodium ions. But on the inside, it's a different story. It's rich in potassium ions, but overall, the inside has a negative charge. And that difference between the inside and the outside, that's everything.
And we can actually measure that difference in charge. For a typical neuron just hanging out, it's about -70 millivolts. Remember that number, -70. It's our starting line. It's the baseline for the entire incredible process that's about to unfold. This state, this stored up electrical energy, has a name. It's called the resting potential. And there's a little molecular machine, the sodium-potassium pump, that is constantly working, like a bouncer at a club, pushing sodium out and pulling potassium in, just to make sure that battery stays perfectly charged and ready to go at a moment's notice. So we've got our charged battery, it's ready, but what does it actually take to flip the switch? See, not just any little poke or prod will do. The signal, the stimulus, has to be strong enough to get things started. This brings us to a super important idea called the threshold. This is the bare minimum level of excitement the neuron needs to feel before it will fire. If a stimulus is too weak, if it doesn't hit that threshold, well, it just fades away. Nothing happens at all.
And there's a magic number for this too. It's right around -50 millivolts. If a stimulus is strong enough to nudge that internal charge from -70 up to -50, that's it. That's the trigger. That's the point of no return. The action potential is now guaranteed to happen. And this reveals one of the most fundamental rules of your nervous system. The action potential is an all-or-nothing event. There's no such thing as a weak signal or a strong signal. It's not a dimmer switch. It's a light switch. The neuron either fires with 100% of its power, or it doesn't fire at all.
All right, the threshold has been crossed. The switch has been flipped. Now for the main event, the show itself. This is the incredible wave-like chain reaction that is the action potential. This whole electrical wave happens in 3 distinct acts. First, depolarization, that's the firing. Then, repolarization, that's the reset. And finally, a brief little dip called hyperpolarization. Let's break down each one. First up, depolarization. The instant we hit that -50 millivolt threshold, thousands of tiny little gates, these are the sodium channels, they just fly open. And remember all that positive sodium that was waiting outside? Whoosh, it floods into the cell. And this causes the internal charge to rocket from negative to positive. Fun fact, local anesthetics, like at the dentist, work by blocking these exact channels, stopping a pain signal before it can even start. Now, this flood of positive charge is so huge that the inside of the neuron doesn't just get back to zero. Oh no. It skyrockets way past it, all the way up to about +35 millivolts. This right here is the absolute peak of the action potential. This is the brightest moment of the spark. But,
What goes up must come down. The moment we hit that peak, the sodium channels slam shut. And at the exact same time, a different set of gates, the potassium channels, swing open. Now, all the positive potassium ions that were inside go rushing out of the cell. This makes the charge inside plummet back down towards negative. That's repolarization. The reset is in progress. Now, these potassium channels, they're a little bit slow on the uptake. They take a fraction of a second too long to close. So a few extra potassium ions escape, causing the neuron's charge to briefly dip even lower than its original negative 70 millivolt resting state. This little overshoot is called hyperpolarization, and it might seem like a mistake, but trust me, it is incredibly important. And that brings us to a really big question. How does this electrical wave travel down the neuron in a clean, straight line? Why doesn't it go backward and just create total chaos? Well, that brief little dip we just talked about, that's the secret. It all has to do with something called the refractory period. This is just a tiny moment of recovery, a little cool down, where the part of the neuron that just fired is physically unable to fire again. It's like a system reboot that forces the signal to keep moving forward and only forward. And there are actually two parts to this. There's the absolute refractory period, where it is flat out impossible to fire again. The channels are just busy. Then there's the relative period. This happens during that hyperpolarization dip. Here, it is possible to fire again, but you'd need a much, much stronger signal to get the job done. So the bottom line is this. Because the section of the neuron right behind the signal is in this reboot phase, the wave of electricity has no choice. It can only spread forward into the next fresh, rested, and ready section of the wire. It guarantees that every single nerve impulse is a clean, one-way trip. So let's put it all together one more time. We start at a resting state of negative 70 millivolts. A stimulus comes along and hits the negative 50 threshold. That triggers depolarization, and the charge spikes all the way to plus 35 as sodium rushes in. Then repolarization kicks in, bringing the charge back down as potassium rushes out. We get a brief hyperpolarization dip, and then finally the pumps reset everything back to resting state, ready for the next signal. An absolutely incredible dance of ions and electricity, and it all happens in just a few milliseconds. And that leaves us with one last big question to think about. We've established that every single action potential is an all-or-nothing event. They are all the same size, the same strength. So, how does your brain know the difference between a soft touch and a loud sound, or a gentle breeze and a painful pinch? Well, that's a story about frequency and patterns, and it's a topic for another day.